Good morning, everybody. We are going to start the first session of today, one of the first sessions, and this will be about hardware masking. We have some technical issues at the moment, but not for this talk. We're going to start a first talk, which is about extending randomness-free first-order masking schemes and applications to masking-friendly boxes. And the talk is going to be given by Lijuan Wu, if I pronounce it correctly. I'm very sorry. My Chinese experience is pretty restricted. Yeah, go on. The stage is yours.
Yeah, okay. Thank you for the introduction. Hello, everyone. I'm Lijuan Wu from Shandong University. I'm very glad to give the presentation about our recent work titled Extending Random-Free First-Order Masking Schemes and Applications to Masking-Friendly SBoxes. And this is a joint work with Yin Hongfan, Wei Jiawang, Bat Prinil, and Mei Qingwang. My talk consists of the following 5 parts: background, new techniques, case studies, security analysis, and conclusion. In this talk, several new techniques will be introduced, such as nonlinear compression layer, joint masking schemes, STP search model, new masking-friendly SBoxes. The first is background, Boolean masking. Boolean masking is an important countermeasure against side-channel attacks. It is based on secret sharing. That is, a secret variable x is divided into S shares, but these S shares satisfy a condition, that is, the SO of these shares equals the secret variable x, like pointer 3. This technique ensures that no useful information can be obtained use partial shares. Next, and CHES 2021. A systematic methodology for constructing two-share random-free first-order masking scheme was proposed for the first time. And this work eliminates the fresh randomness in the masking scheme. It is a very nice work. And the following figure is an example of two inputs and gates. The construction of random-free masking scheme can be summarized as searching for a search of component functions that satisfy masking properties, such as non-completeness, correctness, and uniformity, and so on. Our work extends the search space and enable the construction of more masking schemes. In order to achieve this extension, we introduced several new techniques, such as nonlinear compression layer, joint masking schemes, and so on. The following is our new techniques. The first technique is the nonlinear compression layer. We apply nonlinear options like a quadratic form to compress multiple component functions instead of only linear options. In addition to the linear compression layer in prior work, this technique applies the nonlinear option and extends the search space to nonlinear compression layer and enables the construction of more masking schemes. And the following is an example of two input AND gates. And the compression layer is applied the quadratic form. Yeah. For complex function, like a cubic function, due to the flexibility of nonlinear option, the nonlinear compression layer enables the reuse of component functions in the expansion layer. And therefore, this technique yields more area-effective masking schemes. And in the following, this is an example of two input AND gates with nonlinear compression layers. This is a compression layer. This is nonlinear option. And this leads to a compact implementation. This scheme requires only 6 component functions instead of common schemes, which consist of 8 component functions. And experimental results shows that this scheme achieves a 16% hardware area reduction compared to common schemes consist of 8 component functions in the expansion layer. The next technique is the joint masking schemes. It theoretically suppose linear and nonlinear compression layer, but due to the increased computational complexity of multiple Boolean functions, we focus on the joint masking schemes based on the linear compression layer. We first introduce the share assignment strategy. This technique provide a comprehensive search space for construct masking schemes with linear compression layer. Each drives all possible share assignment types for a given Boolean function from the perspective of correctness. The following is an example. Figure 4 is a one-lead share assignment types for 2 input AND gates because it covers all shared forms of A times B. But in contrast, figure 5 is an invalid share assignment types because it lacks the shared form A1, B1. That is, F3 is around the share assignment types. Yeah. The main idea of joint masking scheme is we consider multiple Boolean function as a single entity to construct a joint masking schemes, and instead of handling each function independently. This idea enables a complex implementation. This technique will reduce reuse. Here is an example for two functions. The two functions is cubic form, and in figure 5, figure 5 is this example. This scheme is the linear compression layer, but in the expansion layer, there requires only 6 component functions compared to common schemes, which consists of 8 component functions. This scheme reduce 25% area. Yeah, next. The nonlinear compression layer and the joint masking scheme extend the search space and offer additional benefits, but construct random-free masking schemes within a huge space remains a challenge. We apply the STP solver to search for the desired masking schemes within a huge space. Specifically, the following is the STP search model, which consists of m+2 component functions, m in the expansion layer, 2 in the compression layer. And each component function is characterized as ANF, and these masking properties, the required masking properties constrains the inputs and outputs of these component functions. Instead of direct exhaustive search, the STP search model began by convert the input constraints into a CNF form, and then use heuristic algorithms to quickly find the desired solutions. The next technique is new masking-friendly S-boxes. Yeah. As the only nonlinear component in the block cipher, S-boxes plays an important role in theoretical security and the implementation cost. As an application, we provide a construct for a masking-friendly S-box with good cryptographic properties and excellent hardware masking properties. The following figure is the workflow of new masking-friendly Xboxes. Specifically, it consists of 3 parts. The first part, we will generate some candidate Xboxes that meet the crypto properties. And the next part, we will generate random free masking schemes for these candidates. And finally, we will filter the desired Xboxes with good hardware masking properties with automated true Genomics design compiler. The following is the case study. In order to highlight the benefits of our techniques, we provide several case studies. The first case is the Prince Xbox and its inverse. Due to the limited search space, the prior work is failed to achieve uniformity for Prince Xbox and its inverse. In our work, we address both challenges. Specifically, for the Prince Xbox, we use the share assignment strategy to find uniform masking schemes for the Prince Xbox. For the inverse of Prince Xbox, we use the nonlinear compression layer to achieve the uniformity. Based on both uniformed Xboxes, we apply the two-share random free mask the round-based Prince encryption and the decryption function in the following figure. Yeah, the next case is the skinning Xbox. In order to expand the search space, we also find some optimized Xbox, particularly the skinning Xbox. Skinning Xbox consists of 2 cubic and 2 quadratic coordinate functions. We use the nonlinear compression layer to the quadratic function and joint masking schemes to the quadratic functions. And the result, the optimized skinning Xbox achieves a 21% hardware area reduction and 15% dynamic power reduction compared to prior work. And in the following, we also provide the two shared random free mask the round-based skinning encryption function. It is without fresh randomness. Some other Xbox also achieved similar optimizations, such as Mastoring Xbox, Gift Xbox, Present Xbox, Mindora Xbox. But for the AES Xbox, the uniformity of this Xbox remains a challenge because the construction. As an example of new masking-friendly Xbox, we construct and filter several new Xbox with good crypto property equivalent to Prince Xbox. The lookup table for 5 of these are provided below, and the hardware performance are also provided in the following figure. As shown in this figure, candidate Xbox S1 outperforms the Prince Xbox and its inverse in terms of area and dynamic power. Yeah. The next is security analysis. We evaluate the security of our schemes from both formal and experimental. For these Xboxes, we use the silver tool for formal verification. For the Prince and the skinning cipher, we use the automated tool Prelude with 10 million simulations for each. In order to verify the practical security of our schemes, we also conduct the FPGA-based experiments. From the following figure, we confirmed the security of skinning cipher with 10 million traces. The following, we also confirmed the security of skinning Xbox with 10 million traces. In conclusion, we propose several new techniques for random-free first-order masking, nonlinear compression layer, joint masking schemes, STB search model, and the new masking-friendly S-box. And the results, we not only construct masking schemes for Prince S-box and its inverse, but also optimize the hardware performance of several S-boxes. And some new S-boxes with good crypto property and excellent hardware masking performance are also provided. Yeah, okay, thank you for your attention.
Thank you. Any questions? We have time for some questions. Yeah, then I start. Can you get back to your slides? I mean, I don't remember the number, but if you go back, for example, here, one of the questions might be that you say that these 5 S-boxes, yeah, there can be alternative to Princess box, right? Which kind of cryptographic properties did you consider for this S1 till S5?
Yeah, actually, this S-box is found with STP server, and we find many S-box, not just the 5 S-box. The 5 S-box is and some example, and then the performance of this 5 S-box is simulated with a design compiler to get the hardware performance.
No, I mean cryptographic properties, not the performance with respect to area and masking friendly. Means that to which, for example, group do they belong, and you know, linear and differential properties for the cryptanalysis. Which kind of properties do you consider for this S1 till S5?
Yeah, the cryptographic property is found with another work. Yeah, we see another paper to get the file evaluate the crypto property with the Princess box.
Okay, are these S boxes are affine equivalent to the Princess box?
Yes, sir.
Okay, good. Then can you go back again to slides? Back. Here, for example, you have in something in I don't have the pointer, but somewhere in the diagram, in the figure, you have input 0 to the multiplexers.
Yeah.
Can you explain that?
Yeah, this is because in the prior work, the compression layer is reused. Why this compression layer is independently? Because the Prince S-box applied the linear compression layer, and the inverse of Prince S-box applies the nonlinear compression layer. So we apply the independent compression layer, and the 0 is used to prevent leakage.
Prevent leakage.
Yeah, prevent the glitch extended probing models under the glitch extended probing model. The 0, yeah.
But 0 goes to the compression layer, and what comes out of the compression layer?
Yeah, if this true, yeah, the 0 is go to the register and to compress, and this case the inverse S is go to the register and the compression layer. So secret information is the inverse of S. Of S.
I guess you mean if a probe is placed on the output of the multiplexer, the large multiplexer, right after the compression layers, then compression layer, after the compression layer, there is a multiplexer, yeah?
Yes.
Then you probably mean that if a probe is placed to there, it should actually propagate backwards to those registers at the input of the compression layers. And then they should be actually independent of the input, and then they should not have information about the S and S inverse. And one of them should be definitely 0.
At the same time, S and the inverse of S is not not at the same time.
At the same time, they are not secure. Okay, good.
Through the circles.
Any other question? Yep, Nico. The microphone is actually in the middle.
Yeah.
I think the microphone is off.
No, it's better. Okay, many thanks for your talk. Just a short question. Where can we find your designs? Are they on GitHub?
Sorry, pardon?
Are your designs on GitHub or publicly available elsewhere?
Did you have artifact for your designs? Are they available somewhere in public? Your designs, your VHDL Verilog designs.
Oh yeah, the source code is provided in the GitHub.
Ah, okay. Thanks.
Okay, thank you for your question.
Good. Any other questions? Then I will actually end up with another one. Get back again as a last question. Back in the slides. Yeah, here, for example. You, if I understand correctly, you have the non-complete list for these component functions, and then you look for the identical joint distribution, which actually is fine, and then finally find something which is correct and also uniform. How large is the search space?
Actually, we experiment the cubic function is enough to search desired solutions.
Okay, how large is the cubic function? How many bits? 4-bit to 4-bit, or even larger functions?
I think the most complex function is the coordinates function of princess box.
Princess box. Okay.
And I think princess box, the coordinate is enough complex.
Okay. How long did it take for you to find some solutions which are correct and also uniform?
Yeah, actually, for the princess box, it takes 2 days.
2 days.
But for the following the skinny S box and my storing gift and so on, this S box will take several hours to get the desired solutions.
Which kind of a machine? How many cores?
The machine is our server with 48 core and 215 file RAM.
Okay, good. Okay. If there is no other question, then let's thank the speaker again.
Thank you.
Okay, we're going to move on with the next talk. Okay, this is ready. The presenter is there. Hi, Wade. Can you try this, whether it works? Yeah, looks good. Yeah? Good. The talk is titled Probing Secure Composability Without Fresh Randomness, Theory and Application of ASCON, and the talk is given by Wade.
I'm here for the introduction. Hello, everyone. Thanks for coming to this presentation, which is about composing gadgets, composing for gadgets in a cipher, again, without randomness. As we see in the previous talk, it was designing gadgets as boxes. But now we are speaking of how to compose them. You know, a single box will not be a cipher at the end, and they need to be work together, maybe hundreds of them. So how we are going to make them work together. This is something that we are going to discuss. And it's a joint work with me and my supervisors, Bart Menik and Leila Batina. Okay, it's no surprise for you the side channel attacks are threatening cryptographic algorithms. And also, you know that the common countermeasure is masking. And masking generally requires randomness. We might be able to prevent using randomness in the level of SBox, as we saw in the previous talk and other PI threshold implementation application. But in higher level of composing them, we might need them. So what do we mean? We will receive shared inputs to operate on. And eventually, the computation will produce shared outputs. This is the game of masking. And one always existing, at higher orders at least, input is online randomness. What is the problem with online randomness? I mean, we are trying to find a problem with it. And the problem is that in resource-constrained devices, such as embedded devices, creating good quality randomness is challenging. Can we avoid it? This is the question that we are trying to address in this work. So our research question is, can we achieve probing security without online randomness? So let's have a closer look to the problem. Then I would say that a standard composition requires refresh gadgets and how they are. In between SBoxes, gadgets, multiplications, sometimes we need to refresh the shares. Otherwise, it will be an aggregated leakage and it will make problem, as shown in various works. So in previous talk, we heard of randomness-free. Maybe another terminology is deterministic masking, in which randomness only comes in with the input shares. And intermediate computations try to avoid use of fresh randomness. And as I said, we are trying to avoid use of fresh randomness inside the masked cipher. So our goal is prove and implement composability without fresh randomness. Then you would say that, okay, that is a very good research question, but it seems to be unfeasible. People have looked into it and have shown that even composing two simple gadgets might get insecure. So you are speaking of composing hundreds of gadgets. What is the guarantee? Yeah, that is the point that I need to add. We are speaking of composability for ciphers, round-based ciphers. So we are going to use properties of ciphers in our benefit. Typically, we don't look at cipher. We say, okay, we don't care about the details of cipher. It is a black box to us. We want just to protect it. But I say that let's have a look to inside. Maybe there's something that we can make benefit out of it. So what is this structure that we are going to take benefit? Round-based ciphers are typically designed in layers. For instance, we have one layer of nonlinearity, which is also known as SBox layer. And after that, there is a diffusion layer. A diffusion layer is a linear transformation that combines outputs linearly and makes the inputs ready for the next round. So we are going to use diffusion layer as an implicit refresh. And this diffusion, we will show that ensures adversary probes across rounds remain independent. And we will characterize capacity of diffusion layer for this purpose with its box linear branch number. So our work shows that security for this composition is described as the local security of the S boxes, and of course local security of this, but this is linear and easy to make it secure. Local security of S boxes, shared S boxes, and the box linear branch number of the diffusion layer. So our contribution in theory is to come up with the composition theorem. And we also show that how gadgets can be made secure without using online randomness. It was exactly similar to what we show in the previous talk. So I will not put too emphasis on that. Our formal results are first order composability, which is already seen in other works, but also higher order, to the extent that a branch number of the diffusion layer allows us. And in practice, we apply this theory to make mask implementation of ASCON, as you know, a lightweight crypto, just recently standards with NIST. So the main theorem that we have is we prove the probing order for this composition, and we show that it is bounded with the local security of the S boxes that are surrounding diffusion, and the branch number of the diffusion layer. So it is upper bounded with the local security, and the lower bounded also with the capacity of the diffusion layer to make the required independence. Okay, let's have a look at how diffusion layer can help us. What's a diffusion layer? A diffusion layer is a linear transformation. I have given a simple linear mapping here, working on 15-bit input, which is 15-bit, is XORed with its circular shifts. So it's a simple diffusion layer. For instance, what does it mean? It means that the bit 0 of output is XOR of bit 0 of input, XOR with bit 14 and bit 12. So it's a parity relation, describing dependencies between input and output. And what is interesting to us? The interesting thing is that we see that there is no parity relation with less than 4 terms. We can write many parity relations and combine them in any way, and at the end of the day, we cannot find something with less than 4 terms. And what does it mean to us? It means that less than 4 probes in the domain of masking, we are interested in probes. With less than 4 probes, if you have just 3 probes, you cannot see any dependency, so they are independent. Since they are linear, there is no linear dependency, so they are independent. And in the scale of diffusion layer, we also need to take into account boundaries of S-box. In the scale of a big diffusion layer surrounded with S-boxes, box linear branch number is defined as the minimum number of active inputs at the S-box plus active S-boxes at the output. So this quantifies capacity of diffusion layer to help probing security. We already saw in the previous talk that input randomness can help to achieve good properties without requiring a new randomness, as it blinds the intermediates that an adversary can observe. So I will do it a little bit fast, because it's already duplicates previous talk. So for instance, if we have a probe that is probing multiplication of 2 shares and XOR with another share, simulation-based approaches would suggest that this probe needs both shares of input B for simulation. Yesterday in the prover talk, we showed that there was a slide saying that mask verif and iron mask are not able to determine security. It is this. They are based on simulation, but silver and prover were not based on simulation. They were based on independence check. So if we go with the simulation technique, which is good, but there are sometimes counterexamples, and this is one of the counterexamples. So it will not be able to identify its security, but at the end of the day, if we go and check independence, this probe is independent of secrets. So in direction of going to deterministic masking, where we avoid any use of online randomness, we should make most benefit of randomness brought in by shares. So it's also one thing that we discuss in the paper, that how input shares can help to achieve security. It was one of the examples. But there are requirements. Probably you will notice that we need the input shares to be independent. Otherwise, they cannot act as a randomness for us. So it's a good time to compare threshold implementation with our approach. They are not much different, but comparison helps to learn it better. So threshold implementation typically is in the domain of a S-box gadget, a small element, not a big cipher, but we are speaking of the scope of a circuit, round-based cipher composing of multiple rounds. So for first order or second order even maybe, they are good. They can go without randomness. But if we go to higher orders, they would typically require randomness. For example, a second order multiplication might require randomness. And for the composition, recent work suggests that composition at the threshold event also will need refresh gadgets. But our main aim is to avoid refresh gadget, which eats randomness. For the cipher level, we know that threshold requirement as uniformity, non-completeness, they are good, but they cannot achieve circuit level. For circuit level, they are also relying on SNI and PNI style simulation argument. But we give a specific theorem that bounds probing security of the whole structure with local properties. So sometimes they require more share and refresh, but ours sometimes win the practicality. And the main difference, I would say, that TI compresses via refresh gadgets, which cost online randomness, and where our approach uses diffusion layer. This is the main point. We also applied this on a cipher, namely ASCON, which is a recent selected cipher with NIST for lightweight cryptography. Its diffusion layer has a box linear branch number 4. And this means in our setup that we can achieve up to third order security, provided that such S-boxes are found. So we rely on other works to found S-boxes. And if they have S-boxes, we have one line of theorem that, okay, use that S-box. And we don't help much, but we just show that if the branch number has the capacity to use it, and you have the S-box, so go ahead, compose them. And in this presentation, in this paper, we have already used first order and second order S-boxes, since they were known. In a recent work, we also found the third order S-box and composed it with this theorem. We had also another observation, maybe useful, And this observation is that we found in our masking schemes that mapping of shares and secrets are somehow independent. You know, we don't care of the mapping of secrets. It is the role of cryptographers to design a good mapping of secrets via the rounds. At the end of the day, no one will ask that why this cipher has no good cryptanalysis properties, why it is linear, why linear attack or differential attack are possible. No one will ask us. We only take care of shares. So we are responsible for the shares. And what we observe is that secrets map non-linearly, that for sure they should map like this, but for the fixed secrets, shares map linearly. And we can use it to verify security as an alternative way. We already gave one theorem and also an alternative way to maybe help to understand it better. And what does it mean? It means that following the rounds, we can characterize input to the rounds as an algebraic form, which has one term as sum of inputs and some nonlinear terms. This sum of inputs is something helpful when we are talking about independence. You know, to the extent that these shares are not used in the second part, they can act as a randomness. Yesterday in Prover talk, we saw that they were speaking of how input shares can play the role of randomness. And yeah, we have also the same message to you, that sometimes input shares can play a role of randomness to the extent that they are not used anywhere else. So this also helped us to verify second order. And just to look at the results, we implemented deterministic S-boxes and composed them via the diffusion layer. We verified them for 1 million traces, and the results are like this. We first implemented first order, then showed that it is vulnerable to a second order attack, as we can find a second order t-test with point crossing threshold with 30,000 traces. But with 1 million traces, it remained safe. It was taking a lot of time for us to collect traces, so we stopped at 1 million traces. And in another work, we showed that in chip whisperer device that we are experimenting, a second order protection is not also enough, because there is a third order attack for that. So we need to move to the third order protection. And with this approach showed significant save of randomness. And you know, even the permutation, initial permutation of Haskell is composed of 12 rounds, each round composed of 64 S-boxes. If it was going to use randomness, it will be a huge amount of randomness, and we are speaking of the scheme that avoids it altogether. So huge amount of randomness. The saved amount depends on the scheme and the order of protection, but at the end of the day, it is easy to see that we are using nothing. So save. So in conclusion, we showed that despite the common belief, fresh randomness is not strictly necessary if we go to specific architectures. We are not speaking of an arbitrary composition. We are speaking of a specific round-based ciphers. And in these specific structures, diffusion layer is acting as an implicit refresh gadget, linearly combining output shares and make them ready for the next round, such that an adversary with limited number of probes cannot tell them apart from true randomness. So if adversary had more probes, can say that, okay, it is not true randomness. You are exhorting something and telling them to me. So there is dependency. But with limited checkpoints, this dependency cannot be identified. And so in this way, our framework demonstrates composability without online randomness. And this opens the path for more resource-friendly protections. And thank you for your attention. And our GitHub code is available here.
Thanks for the talk. Any questions?
Thanks, and nice work and nice talk. Your examples, the S boxes are always quadratic. Does it work also for higher order, also higher algebraic order, your methods? I mean, not the framework, but would you find this randomness-free decompositions of higher order?
Very good question. And very, I would say, let me reach to the point, yeah. I would say that yes, it's a good concern that, okay, capacity of the diffusion layer may allow to go higher, but do we have them? Do we have enough S-boxes at the moment? I would say for some ciphers, yes. For the ASCON that we selected, we were lucky that there are such S-boxes, first order, second order. We already
I meant algebraic order, so the AES, for example. So
these S-boxes are simple enough. For example, they are just one and, so they are second order. So for them, yes. But maybe for a complicated S-box like AES, no. We don't know how to, we are not aware of such S-boxes, and probably they don't exist. And so then the question will change. Okay, you are saying about the framework for the structures that they rarely exist. Even for AES, maybe they don't exist. In the paper, we also give a idea that how we can use randomness, how we can recycle randomness for using S-boxes. Maybe you say that, okay, give me just 2 shares, I can produce a good S-box for AES, but and I don't need to save these 2 bits. In the paper, we give also a recycling approach that how we can use diffusion layer to recycle some randomness, limited amount of randomness, and feed them to S-boxes. So for the framework, we don't need randomness, but the framework depends on existence of S-boxes, which in our case, we were lucky that they exist, but in general, they don't exist. So they require randomness, and we say that how framework can be applied to that cases.
So you are pessimistic about AES because there's no, in the big S-box, there's no refreshing, no diffusion layer in between. Also you think for some it works, your approach, and for others it won't.
Yeah, AES is very complex
Okay.
and difficult to make it, for example, bit sliced, and degree is high. ASCON is simple, just one multiplication.
Okay, thank you.
Thanks.
Okay. Any other questions?
Yes, thank you for your talk. I have one question to your case studies. Are these measurements on hardware or is it software?
It is chip whisperer software, ARM Cortex M4.
Okay, so you haven't implemented them in hardware and measured them, but...
Yeah, it is mainly because when we speak about probing, not extended probing, glitch extended probing, we mainly target software.
Okay.
Hardware, it is much more difficult.
Then why do you compare your scheme with TI?
Yeah, good question. The problem is that TI is the closest family member. They also have a lot of randomness-free structures. So the idea of avoiding randomness appeared first with TI. So we had also this issue while presenting the paper that the boundary with TI should be made clear. Yeah. TI is in a gadget level. Our work is in a circuit level. So we can avoid comparison. Okay, different domains.
But why do you think that your scheme is not gadget-based? Because you are dealing with particular box designs, and then you compose them, and then there is a diffusion layer in between, right? I mean, why do you think that your scheme is just circuit level, it's not gadget-based?
We use existing, if exist SBox, shared masked SBox, as an input, and say that if they are available, then we come in and we say that, okay, these existing SBoxes can benefit with the diffusion in the cipher.
What is the criteria for you that you always say there is an Xbox? What is the criteria?
Because at the beginning we define deterministic, which is a big name that we will avoid any randomness. Okay. Then later we get in trouble. Not all ciphers support. Not for all SBoxes we can find. So to make it clear, we say, okay, deterministic can be the big picture, but our work is not at that end. So for some ciphers, it was successful, but I would say that we were lucky. Not for every cipher it can apply.
Okay, thank you so much. Let's thank Wahid again. Okay, we are getting to the last talk of the session. Yes. The paper is titled Efficient and Composable Mask AES Box Designs Using Optimized Inverters, and the talk is given by Vedat.
Okay, hello everyone. You can hear me well. So my name is Vedat, and I'm presenting this work, which was done in collaboration with my now former PhD supervisor, Roderick Bloom. And I'm very good at naming things, as you can see. So efficient and composable masked AES SBox designs using optimized inverters. So there's a couple keywords, and we will see how they play a role in the paper. As we have all seen in the previous talks and previous days of the conference, differential power analysis is very dangerous for cryptographic implementations because hardware leaks information about the keys through power side channels. An attacker would record lots of power traces, then they would guess intermediate values, correlate them to the power consumption, and then effectively read off the results. And what people came up with was masking. So you split secrets into multiple shares, and then you make sure that your shares are uniformly random, and you try not to combine too many shares at a time while you're doing your computation. And a couple of ways of masking have cropped up over the years. One of them is gadget-based masking. This is where you mask small components, and then you compose them into like the full circuit or the full computation that you want to mask. They have many advantages, such as a modular design, so you only need to design the gadgets and then you just plug them together. It has easy security proofs through composition, so if your gadgets fulfill certain nice properties, such as SNI or Piney, then you can plug them together quite easily and get a full computation that's securely masked just by the composition rules and the security of the gadgets. However, as we have heard in the previous talks, these things consume a lot of randomness. And also they add latency. So you when you use gadget-based masking, you're kind of bound to the complexity of the functions that you're masking. If you have a very complex function, then the latency is going to be high. If it's a very simple, like a quadratic function, then the latency is going to be low. And in this paper, we tackle some of these challenges for the especially important case of AES and the AES S-box. So we present a new design for the AES S-box that kind of has an optimal multiplicative depth, making it lower latency when used in gadget-based masking. And we present new and improved versions of known mask gadgets for field multiplications. In this case, this is this HPC 3.x. And we present 2 ways of soundly reusing randomness without getting into trouble with all of the people that care about proofs. Good. So this is going to be a quick primer on how algebraic degree and latency in gadget-based masking are kind of linked. For affine operations, so also often called linear, which is like field addition, which you can think of as XORs, scaling with constants, and sum of the powers in a particular field. These operations do not add any latency, as they are just composed of a bunch of XOR operations or a bunch of additions when you're in a higher field. And they don't give you any latency penalties, so you can implement them with 0 cycles of latency. For nonlinear operations, it's more complicated. These operations are, for example, field multiplication. You can think of this as AND gates on a bit level, or most powers in larger fields. And here the rule is that the latency is greater or equal to the multiplicative depth, depending on the gadgets that you use. And this is greater or equal to the ceiling of the logarithm base 2 of the degree of the function that you are masking. Here is an example. So this is one of the functions that appears in the ANF of the AES S-box. This is a degree 7 function, so you're multiplying together 7 bits. And since we know that the log of 7 base 2 is like larger than 2 and less than 3, if you take the ceiling, you see that the best you can implement this is going to have a latency of 3 cycles, because you will have 3 levels of multiplication. Here is an example where you first go ahead and multiply the first 2 bits, then the second 2 bits, then you multiply bits 4 and 5, then you multiply the result with bit 6, and you multiply the result of the first 2, and then the last 2. This gives you like 3 levels of this tree of multiplications. And I got really interested in the AES S-box. I always wondered how Kentwright figured out to do this thing efficiently. And this is how it looks pretty much. So you have 2 inputs that are like 4-bit elements, this gamma 0 and gamma 1. So these 2 together are your input to the S-box after a linear transformation. Then you have like a multiplication of the 2 inputs and an addition of the 2 inputs. Then you scale the upper one by this pi squared, which is like just a constant. You square the lower one, multiply it with some other magic constant, add them together. Then you do an inverse in the Galois field with 16 elements, so a 4-bit inverse. You multiply everything with the original inputs, and you get your S-box outputs. And now the question is what are the algebraic degrees of these intermediates, and what is the multiplicative depth? So when you start, you have multiplicative depth of 0, and you have a degree of 1. So these are just some bits. After the multiplication, you have a quadratic function that has one multiplicative depth. The other one is just an addition, which does not incur any multiplicative depth. And then you go along. All of these operations here are linear, and they give you like just no change in these two quantities, except where you have the addition. There you kind of take the maximum of the degree. So it's going to be a quadratic function with multiplicative depth 1. Then you get to this like inverse, which is a cubic function. So it's gonna, like you have a cubic function that has an input which is quadratic, so your output is gonna have degree 6. And the best way to implement this is gonna have a multiplicative depth of 2. So you have a multiplicative depth of 3 for the output. And after another multiplication, you have a multiplicative depth of 4 and a degree 7. And this is kind of sad, right? Because we just now showed that if you have multiplicative depth of, if you have a degree 7, then you can get a multiplicative depth of 3. But here we have 4. And I tried to figure out for a long time what was the culprit. And it appears to be this, this inverse. So when you cut the design in half and you pretend that the first half doesn't exist, here you have like a first degree or like a linear term, linear term, linear term. Then you have like a cubic term after this. And then you have multiplication between a linear and a cubic term giving you a degree 4 term. Meaning that it must be possible to implement the second half of the circuit with a multiplicative depth of 2 instead of 3 like we saw just before. Which means that we need to do a rewrite. We need to figure out a clever way to implement this part of the function such that it gets this optimal multiplicative depth. And I will spare you all of the details. This is how the new kind of design looks like. Effectively, what's happening is you're splitting up this inverse, which is like the 14th power. You're splitting it into to the power of 4 and then to the power of 10. And this gives you power 40, which when you reduce gives you power 14. This, we can verify that it has the correct kind of properties that we want. So the 4th power is one of these special powers which is linear. Then you do a multiplication, you get a degree 3 polynomial and like a 2 multiplicative depth function. You do this power of 10, which is a quadratic function. This changes your degree from 2 to 4, like it just multiplies it. And it can be implemented with 1 multiplication. And then you do this special multiplication at the end, which is just like the normal one, except it's cheaper because this power of 10 has some weird properties. And you end up with like a multiplicative depth of 3 and a degree 7. So this is exactly what we want. We managed to find like a structure for the ESS box which achieves the optimal multiplicative depth, and it implements the function correctly, meaning that now if you do gadget-based masking, you can get a latency of 3 clock cycles for the ESS box. And this is good. So this was kind of the first piece of the puzzle. The next was, I was always wondering why these gadgets work like they do. And I investigated. So we have this HBC3 gadget, which was the first Piney gadget in the glitch extended probing model that has the latency of 1 clock cycle. And we did some improvements. We generalized it to work in arbitrary fields. This was the easiest part. Then we restructured it to like use the field multiplications in a better way to save area and yeah, especially in higher degree fields like we have in AES. And we showed that we can reuse randomness. I will not talk that much about the randomness reuse in the presentation. Effectively, when you have the same input multiplied twice, you can reuse half of the randomness of these gadgets. And this saves you randomness and shares them across multiplications. And I also found one a variant that saves randomness directly. Good, and I will take you on an excursion of how this rewrite looks like. So we start with HPC3. It has these same domain terms that you put into a register. So A and B are the inputs, the indexes are the share indexes. For the, this is like a degree, like a 3-share variant. Here we first take the share I, we multiply it with the second share blinded by some randomness, and we XOR it with another randomness that blinds this correction term, not A0 and the randomness from before. And the first thing that we noticed was you could just remove the negations. So the negations are an artifact of the design of HPC3, which was derived from HPC2, I believe, which really required these negations, but HPC3 does not. So if you remove them, everything stays correct, everything stays fine. You don't break anything, and you do not change any of the security properties. So that's what we did. Then you notice that nothing that's field 2 specific is left. So you can replace the XORs with additions, and you can replace the AND gates with multiplications, and everything stays fine. The only thing that you need to take care of is these randomnesses P that you need to negate in some places to keep this, the correctness property. But other than that, you can just replace everything with additions and multiplications, and it stays correct and secure. And the last thing that we noticed was this A0 is multiplied with multiple terms. And there we can just do a factorization. So instead of having like these 3 multiplications here, we can have 1 multiplication of the sum of these terms, which then looks like this. So this is how we got to HPC 3.1. Also very creative naming, but it saves a lot. So you already see I can fit it into 2 lines instead of 3 from before. You can go even further, so you can reduce the randomness even further. You can notice that these randomnesses are like, you need a quadratic amount of them, and you don't need this actually. So you can just replace them with normal index randomness, 1 for each share of the input B, and everything still is fine. And you see that this saves you some randomness when you go to degree, so when you go to protection like with 4 shares, because here you only need 4 of these R randomnesses instead of, I believe it was like 4 times 3 divided by 2 is 6. So you save 2 bits of randomness for like the 4th protection order. Good. These are the costs of these things. So we start with HPC3, which is like has this many registers at the start, and HPC 3.1 does not save you anything. However, it saves you on field multiplications because we did that factorization trick. So it saves you there quite a bit, almost half. And for the additions and the randomnesses, you don't save anything with HPC 3.1. With the 3.2 variant, which I'm not going to talk about here, this is a trick that I saw from the Compress paper that Guiton did. There you can kind of move the same domain term into one of the cross-domain terms and save some things. The HPC 3.3 variant saves a bunch more. So it saves you a bunch of registers, first of all. Then it saves you also on additions, and it saves randomness. Good. While maintaining the same Piney composability properties. This is how the new masked AES design looks like when you actually write it out. I really wanted to have this in the paper, And it was a pain to draw, but this is how it looks like. So you first have this inputs, gamma, you place them into registers, and then you have this HPC3.x, you can use whatever were the x. And then you have the first linear parts before you get to the second stage of the nonlinear part, where you have these HPC3 gadgets all in parallel. Then you have another linear part, and then you have this back HPC3 gadgets that do the final special multiplication that I talked about earlier. And here you also see that you can reuse randomness in a bunch of places. For example, this R randomness for the second layer can be reused everywhere. So this gadget can use half of the same randomness as this gadget, can use half of the same randomness as this gadget. And the same is true in the very last layer. So in the last layer, because here you have one point that you multiply with all of these other terms. If you go back in the presentation, this is this point here. So here you have like a 2-bit number that you're multiplying with 4 different things in these special multiplications. And you can reuse the randomness across all of them. So these all use the same kind of first stage randomness. The results are very good. So you do have some savings compared to other works. For like spatial reasons, I only include the compress Kent-Wright construction here, where, for example, we save a bunch of randomness. We save 11.1% randomness, so going from 36 to 32, or going from 36 to 29 in this like latency 4 variant that we also have in the paper. And the area savings are also quite substantial. For example, you save anywhere between 3% and 8% with the first design that is by 1 clock cycle faster. So you save area and also latency at the same time. With the second design, you save even more area, like you save 20.7% of the area if you have very large protection orders. Yeah. And with the PRNG, here we just adjusted for the size of the PRNG that you need to produce the same number of random bits. Here we see that the savings are a bit less than without the RNG. This is because the designs still consume a lot of randomness. Good. Conclusions. I would highly suggest all the intermediate level PhD students to not always listen to their supervisors. Like, if they tell you, okay, AES has been masked countless times since 2000, like all of the papers do it, you can not find anything new, I suggest that you don't listen to them. There's always something new if you do a deep dive. For example, you can find a new AES structure, which was not known for, I don't know, 20 years. You can find better gadgets. Like even the HPC 3.3 gadget is relatively new. Like, it's not in the paper. If you look at the paper, it's not in there. I will put it on archive. I don't care to write another one with like a minor change. So you can always make these things better. You can strive to improve things. And you can have efficient composability. This is feasible. So at the time of writing the paper, this was the smallest low latency masked AES SBox, while also being Piney composable. So these things are feasible, and we should kind of invest more in them because they are a proven way to get security without like thinking too much, right? Good. This has been my presentation. I thank you for listening, and I'm open for questions.
Okay, we have time for 1 or 2 questions.
Thank you for the representation. And I wonder how many cycles will be needed if you are using the SBox to build a round-based AES.
Oh, okay. To build a round-based AES, well, it depends on how many SBox instances you have. So if you use like 20 SBox instances, 4 for the schedule, 16 for everything, you will need 10 times 3 plus some epsilon. So you will need about 40 cycles, I guess, if you use like 20 SBoxes.
Do you think it will be 31 or 41?
It will be somewhere in between. I don't know. So if you think about it, it should be like 30 something. Yes.
I just want to, should it is necessary to store the round results in the register, do you think?
Okay, that's a good question. The quick answer is yes. So when you look at the paper and all of the proofs, this has proven to be tiny. However, since you will be wait a second. So since you will be like using the output of one round as the input of the next round, and this will be like cyclic, after some diffusion, you will need to do like an opiny construct, meaning that you need to put it additionally in registers afterwards and possibly refresh to get like transition effect security. Yes?
I don't think so, actually.
No? Why not?
You have a loop, and you have 3 register stages in the loop. You don't need opiny. And it will be enough for 3 registers inside your SBox. Then 31 clock cycles should be enough for the round-based implementation.
That also sounds reasonable. I would have to check it. So, yeah, thanks.
Thank you. Thank you.
Any other questions? I have a short question because we are going to actually start a coffee break.
Yes.
That was about, can you get back to your slides?
Which one?
I think here, no, here, next one. No, forward, not backwards. Forward?
Yes.
Here. You talk about reusing of the randomness.
Yes.
This is particularly relevant for this design, or no, every HPC3X which is in parallel
Yes.
can share some form of randomness.
Pretty much, yeah. So this happens because you are multiplying the same things by different amounts. So here, for example, you have this wire here that you multiply once with this gamma 0, and you multiply another time with gamma 1, meaning that if you pick the inputs correctly, if it picked this as input B, then you can reuse the randomness that you use here, this R1, you can also reuse here. Yes.
This is completely independent of the next function, which actually combines the output of these gadgets.
Yeah, so it does not matter if you combine them afterwards. There is one caveat: you cannot have them sequential. So the things that you combine have to be in parallel. So if you have this here that's multiplied with something to get this, and then this is multiplied with the same thing, and you want to reuse here, that would be wrong. So you have to reuse them in parallel, like have the same input going to 2 different outputs, and then you get this kind of meta gadget that's composed of this thing here and this thing here that's also a piney gadget. Okay. So that's kind of the way you have to reuse it. This is not only applicable in AES, you have this in many circuits. A good example for this would be like addition circuits that you need for various ERX ciphers. Because additions, when you look at the Cogglestone or the, like, how's the other one called? Like a bunch of these parallel prefix adders use the same input into multiple AND gates, where you can also save the same kind of randomness.
Okay.
Yeah.
Thank you so much. Let's thank the speaker of the session again.